Chapter 7 in the sensors class talks about infrared radiation thermometers. At the beginning of this chapter, we just talk about the electromagnetic spectrum. Our visible light is only a small slice of the electromagnetic spectrum. In addition to that, we've got everything down to extremely high wavelength, like 100,000 nanometer wavelength infrared, through visible light, ultraviolet, all the way up to X-rays with extremely low wavelengths. So X-rays are the most penetrating because they have the smallest wavelength. So that's why we use X-rays to kind of bounce off and through humans. And if you bounce off something, it's probably a hard structure like a bone. And that's why we use X-rays for that. Very, very high nanometer wavelengths, high wavelengths tend to penetrate less. The longer the length, or the shorter, smaller the nanometers, then the more it tends to penetrate. This is the spectrum. So you guys all understand basically how radiant thermometers work. You've got a sensor that receives in all the light rays like a camera. Everybody has a camera. You guys are all used to how this camera works. On the back of your cell phone, for most people, is a camera, and is there a little chip in there that receives all the light that bounces on it. In fact, not just a single cell, it's literally got a huge number of light sensitive cells, and then by building up a picture of those cells, you can build up a video or still picture of anything you point your phone at. So that's how all these radiation things work. They use chips of some sort to receive the radiation and record it. A lot of these things have to do with how that radiation works. So we're going to learn a little about the basic radiation, all light radiation in this case. And we're going to learn about something called a black body. And why are we learning about this? Because they're useful for calibration. It's an ideal body that absorbs all radiant energy of any wavelength falling on it. A gray body emits and reflects a portion of all wavelengths equally. In other words, it reflects up and down that spectrum equally. There is no such thing as a true gray body. A non-gray body is a body that emits and reflects radiation to a varying degree depending on the wavelength of the infrared, so it'll reflect more or less depending on the wavelength. So if I have, say, a bright red surface, like my little dictionary here, that bright red surface does a really good job of reflecting light in the red wavelength. So when I bounce white light on it, or slightly yellow light here, it bounces back stuff in the red spectrum, which is in the kind of 750 to 700 range. And that spectrum, then, this is really good at bouncing back. That's why I see red. That's how light works. The stuff that bounces back makes the thing that you're looking at a certain color. Emissivity is the ability of a body or any surface to emit radiation, and is the ratio of the emissive power to the emissive power of a black body. So you're just comparing it to a pure black body with no reflecting at all. Reflectivity is determined the body's ability to reflect it, and it's sort of obvious. If you've got a matte black surface, it's not going to reflect well. If you got reflect well at all. If you've got a shiny stainless steel surface, for instance, it's going to reflect a lot of the temperature. Any of the radiation is going to bounce off of it, and to a high degree be reflected off of it in the visual spectrum primarily. And guess what? It's going to be hard to use a radiant temperature sensor on anything with a high degree of reflectivity. Transmissivity is the ability of an object to allow radiance to pass through it. Glass, for instance, has a high degree of transmissivity in the visual spectrum. However, most of our modern glass has got coatings on it to keep it from transmitting radiation in the infrared spectrum, so we don't lose heat out of our house and we don't have the sun's light cook our furniture. So here we have a few other key thoughts about background temperature compensation. You guys can read that. There's some important stuff there. So the next section starts at the bottom of 70, IR thermometer construction. There's a few different kinds of IR detectors out there. A detector is simply the thing that actually does the measurement of the radiant energy. And we can either have a one color or a two color IR detectors. The cheap ass detectors we normally get, and actually let me go grab up one of those. I got them right over here. Hold on. These detectors right here. This is a very inexpensive detector I picked up, I don't know, in Canada 5 years ago or 4 years ago or so, I forget when. And you basically point it, it's got a single one color detector. You shoot it and it gives you a temperature measurement, right? That's great. That's what a one color, single color IR thermometer does. We can have something special called a two color thermometer. That means it's got two chips inside of here, and they're set up to measure across two different sets of wavelengths. That gives me advantage in that if I've got some sort of material that's blocking my IR beam, like some mist or smoke or dust, then I can set this up to automatically account for and be more accurate in that sort of atmosphere with multiple things between me and my target. So you're not going to see those two color thermometers in use very often, except for high dollar industrial applications. So obviously we can hook up our IR sensors by the use of a fiber optic cable, and that's one way to do this. We have the need for isolation, so you guys can read about that. We're going to skip over pyrometers because that's an old school technology. The version 6 of the book goes into a little bit more detail, and they actually have a little more description about pyrometers, I think. A pyrometer is simply a way of measuring very high temperatures by the use of the color of a filament. Actually, it's still here in this book here, bottom page 75. You can see this filament when the background color is hotter than your filament. You'll see the filament kind of appear in black. When the background color is darker than your filament, the filament is actually warmer than the background color. And then when they're matching each other, the filament disappears. That tells you that the background temperature is the same as the filament temperature. It's just a very old school, cheap way of doing temperature measurement for like furnaces and that sort of thing. Thermal imaging is the latest technology. You're going to see a lot of handheld devices. Like this thing might have cost 35 bucks. A good thermal imaging device will be giving you a full 3D picture, like this picture right here, or at least a 2D picture with depth. And they're used all over the industry. They're good. They're used in housing applications where they're checking for heat loss. They're used in by electricians to see if they can find shorts and problems with electrical connections. They're used in manufacturing processes where you want to spot the temperature of your process. So this is basically a high dollar imaging device. It's really, really good.